Sapphire is really a series of 6 experiments, all aimed at spacecraft fire safety. Fire safety has been a big concern ever since we started flying crewed vehicles into space. A lot of research has been done. The trouble is there's always a crew around, and you've got to put it into a chamber and keep it confined and safe from the crew. Well, that's where Northrop Grumman's the Cygnus vehicle comes in. It's the perfect vehicle for us to do what we really want to do, and that's burn larger samples, because it docks to the station. It ends up being filled with trash. The crew closes the hatch, and when it does, it's at 1 atmosphere and 21% oxygen, and then it goes away and nobody's on it. When we ran Sapphire 1, 2, and 3, the sizes of the samples, instead of running something the size of a note card, was really something about the size of this, about 1 meter long and about 4/10 of a meter wide. What we really want to do for Sapphire 4, 5, and 6 is to take what we've learned here and really make a more sophisticated experiment, and then also some of our tests are going to be conducted at a low pressure, about 8.2 psia and 34% oxygen. And if you know things about combustion, you start increasing the oxygen level, the fire should become more energetic. And those are the kinds of things that we're going to be doing on Sapphire 4.
A bacteriophage is a virus, but it's a virus that only targets bacteria, not our cells, not human cells. So it's these bacteria that are the prey to this predator being the virus. Phage technology and looking at and trying to develop phages can be a new and novel approach to targeting and getting rid of pathogenic bacteria. If you take a general antibiotic right now, most of the bacteria get targeted. Well, what if you could develop a phage that was highly specific to just the pathogen? Now you keep your gut microbiome intact, you don't harm everything else, but you get rid of that harmful bacteria. Now when you put it in space, now we get a new environment. Because in space, the one commonality about space is that biology changes. So in this interaction, we know that the target, the host, the bacteria, which is E. coli, grows faster. Will the phage become more lethal? Will it become more specific to its prey, its host, it's the target, the bacteria? Or will the bacteria win and become more resistant and be able to shed away and get away from that virus? How does this happen in space? We have no idea. That's why we go to space to do this project.
Space provides a really unique environment to study phenomena like bone and muscle loss, because things happen so much faster. And that increases our ability to assess drug therapies and exercise programs that can mitigate the loss of bone and muscle.
Bone is a living tissue. It's not a static piece of rock that's in your body.
What we're looking at is that pre-osteoblast. Those cells are on the verge of being a mature bone cell, which can produce a lot of the bone matrix that mineralizes and becomes solid bone. The question is, how does spaceflight and microgravity specifically affect the changes in this gene expression?
But the other thing we're going to be looking at is metabolic pathways that's occurring on the space station. And that actually follows on with the genomic studies that we're doing. So it gives you a more complete picture of what's happening to the cells.
This flight is a second time up for us. We flew an experiment using these cells back in 2016. In this case, we're looking at a much tighter environment, and we have a greater number of cultures as well.
This is a scanning electron micrograph that I took from some debris that was collected by our crew members. So currently the ISS has a blind spot in which we cannot perform this analysis on orbit. And it takes quite a while to get this debris back on Earth. And it's an even bigger problem when sample return is not an option, such as for deep exploration space flight.
So for the past few years, my small company Voxa has been working together with NASA to extend the capabilities on ISS to be able to identify and study the structures of very small scale. For small scale, we're talking about things that are on the order of 1 to 10 microns and maybe even smaller than that. And this is a terrestrial instrument that we developed initially and extended its capabilities with NASA. The strengths of electron microscopy are twofold. The first is the ability to see very, very small structures and down to the nanoscale. And secondarily, it has the capability of identifying the chemical composition, in particular the atoms and the quantities of atoms inside that structure.
Looking ahead, when we start going to the moon, building Gateway, and eventually to Mars, this platform, which is really a research platform for future exploration, will aid in a number of different ways.